Welcome to the DSA series. In case you're wondering what you're doing here, I'm sure you're interested in DSA, data structure and algorithms, which is why I've stumbled upon this video. In case you're wondering who I am, my name is Kallol Bhattacharya and I have been in the IT industry for the past 24 years, recently retired. And I thought that my knowledge in the IT industry is best put to use if I am with you and I'm trying to impart whatever I have learned in terms of these lecture series. DSA, Data Structure and Algorithm, is going to be an exciting series, and we will cover everything from the basics of DSA to the advanced concepts of DSA. We will cover a plethora of questions that are typically asked in the university curriculum. So anybody who is interested in DSA as a topic, as a subject, anybody who has DSA in their university curriculums, they can definitely benefit out of this. Be with me. I'm sure this is going to be an exciting journey in order to prove how and what modern algorithms can do. Thank you so much.
Hello, welcome back. I'm sure all of you are doing well. Let's study DQ and priority queue today. So we had started with the DSA lecture series some time back, and we have covered a whole bunch of queues and stack related stuff in the previous lectures. Feel free to watch it. But today's session is mostly going to be around DQ and priority queue, and this is what we'll typically cover. So we have finished all of this, right? So we have finished all of this. And we are going to touch upon DQ, priority queue, and the operations and the algorithms on the operations of DQs and priority queue today, which will typically complete our module 2, which we targeted to complete in terms of our syllabus. So any particular university curriculum will have stacks and queues, and with today's lectures, we'll be completing both of them. Now, what will be covered here today? As I said, we'll cover DQ, we'll cover the operations, their algorithms and the complexities, we'll cover priority queues, the operations, algorithm and complexities. And then of course, we will wrap it up by solving the common set of problems that are asked in any typical university curriculum. Right, so let's start with DQ first, and then we'll get into our priority queue. So DQ, if we have to define DQ, then this is the definition of DQ. Insertion and deletions are allowed from both the ends. That's the one unique part of DQ. And the second unique part of DQ is that it behaves like a stack as well as a queue. Now, what does these two things mean? Let us try to figure that out. Insertion and deletions are allowed at both the ends. Now, if we talk about a queue, the deletion from the queue, the exit from the queue always happens from the front. So if this is my front and this is my rear, right, then my exit will always happen from the front. So this is my DQ operation, right? So don't confuse DQ queue with the DQ operation. In fact, for that matter, let me also not confuse you and talk about this as let's say delete, right? So the delete operation of a particular queue will always happen from the front of the queue. That's what we knew. And the entry operation, right, the entry operation of the queue will always happen from the back of the queue, which is the rear of the queue. And because we are naming this entry, let us name it a suitable opposite word, which is basically exit. And I'm just trying to do it to avoid being confused by DQ and NQ for that matter as the terms of the operations, because the queue today we are discussing is called DQ. And by the way, what is DQ? DQ stands for double-ended queue. So double-ended queue is what is DQ, and because of the word D and E, we are calling it as a DQ, right? So that's what typically the acronym of DQ means. Now, the standard queue has this particular architecture where we have a front, we have a rear, we have exit operations from the front, we have entry operations from the back. Now, if we are actually saying that no, we are going to have some queue which will also have entry operations from the front and exit operations from the rear, then basically we are opening up both the ends for both entry and exit, and hence the word double-ended queue, and that is a DQ. So this is basically a DQ in terms of the architecture and the way it behaves. Now, if we actually talk about LIFO and FIFO, now if we understand that because it has opened up both the ends and it allows for entries into the front as well as the rear and exit into the front from the front as well as the rear, then can we imagine a DQ to be something like this, where entry happens from the front. So this is our front, this is our rear. Entry happens from the front and exit also happens from the front. So this is my entry and this is my exit. If this is the case, then we are talking about a stack here, because I am only, if you just imagine this entire horizontal structure as a vertical structure, you will understand that it behaves like a stack, that at the top of the queue, the front behaves as the top of the queue or the top of the stack, and at the top of the stack we are allowed to enter and we are allowed to exit only from the top of the stack. So if the front starts behaving like a top and you have prohibited the entry and exit from here, you have prohibited the entry and exit from here, then the DQ starts behaving like a stack, right? So if that is clear, then of course we can make it behave like a queue now. If I just say that which we in fact talked about, that I will allow it to exit from the front, I will allow it to exit from the front, and I will allow it to entry from the back. I will not allow the other two operations, that is the exit from here and the entry from here, right? I'm sorry, this should be entry, so let me make it as entry. Yeah, so the entry from here and the exit from here will not be allowed, and if that is not allowed, what do we end up with? We end up with a queue. So in a sense we can say that a DQ behaves like a queue, behaves like a stack, provided you restrict certain things, right? Provided you restrict certain entries and exit, because it allows both entries and exit at both the ends. Now if we restrict certain things, then we actually land up in actually getting into something called as an input restricted and an output restricted queue. So as we know that a queue will have a DQ will have an entry from this side, an exit from the same side, an entry from this side, and an exit from this side. Now if I say input restricted, that means that I am going to remove one of the input, one of the entries. So I can say that I will remove either this entry or I will remove this entry. Now if I remove this entry, then this is an input restricted queue, right? And if I keep this entry and I remove this entry, then this is also an input restricted queue, because you can enter only from one side but exit from both the sides, right? And if we actually talk about output restricted, it is going to be the reverse. So if I have this as the standard input and output, and if I can actually restrict the output, I will have two outputs here, I will restrict the output here. So I will say that I'm going to remove one of the outputs. This is an output restricted queue. If I bring that back and restrict the output from here, this is also an output restricted queue. So that's on the DQ types and the DQ definitions. Now let's come to the DQ operations. Now a couple of operations, in fact most of the operations is going to be similar as that of the queue operations, which you have already understood if you have visited the last lecture series. If not, please visit that video and understand the operations when we talked about circular queue, the operations around it, right? So what we are talking about here today is that, let's assume, and by the way, DQ will be represented in a circular queue manner, and it will be tied, the front of the queue will be tied to the back of the queue in order to take advantages of what we learned in the circular queue in terms of space, in terms of infinite entries, and so on and so forth. That was already discussed in the last lecture series. Now if we talk about the operations, the first operation we are talking about is insert rear. So of course insert rear is the standard operation. So if we have a queue, let's say that we had a queue like this, right? If I am inserting from rear, that is my standard operation of a queue. So what we are discussing now are the standard operations of the queue, and then we will talk about the special operations of DQ. So the standard operations of a queue, in that, if we have to talk about insert rear, then let us do one thing. Let us follow these insertions and let us see that how the algorithm actually handles those insertions. So for example, it says that insert into 20 into the index position of 0. But I am not saying index position of 0 directly. What I am saying that insert rare int x. So in this case, x becomes 20. The queue is full, no. So it goes on to here. Front -1, front equal to 0. If you remember from our earlier algorithms, front and rear are always set to -1. Front and rear are always set to -1 for an empty queue. Right? So front and rear are always set to -1. And if front is -1 and it is empty, we have to put front equal to 0 in order to move front. And why is that so? That also I explained in the last lecture. See, when we are actually talking about a queue, then the front stays here, and if we talk about insert rare as an operation and we start inserting elements like 32, 5, right? What is moving? Front is not moving, the rear is moving, right? So rear comes here, then rear comes here, front was here, rear was here. Front stays static and rear only moves. So insert rear actually handles R. Insert here rear doesn't handle front, right? So how will front, which is -1, be adjusted? How is front being -1 be adjusted to 0 when insert rear is getting called repeatedly? Somebody has to take care of front becoming 0, because rear will become +1, +1, +1, +1 as you move forward in the queue and insert elements into the rear. Front doesn't change. If you have to change front, then that is only for the first time. And that's the way in order to remember this entire thing, is that when we are talking of insert rear, who is not handled? Front is not handled. So take an exception. The first step is take an exception for front getting handled. If front is -1, make it 0, because thereafter front will never move. But somebody has to take the responsibility of moving front one time when insert is happening. Right? So that's what you are doing here. So that's what we did. So if we have inserted 20, then what we have achieved, we will come here, front is -1, and if front is -1, then we make front equal to 0. So front comes here. And then what does rear become? Rear becomes rear plus 1 modulo size. Rear was what? Rear was also -1. -1 plus 1 is 0. -1 plus 1 is 0. 0 modulo size of the queue is 5. So 0 modulo 5. So size of the queue is 5, and 0 modulo 5 is 0, and that's why the rear also comes here. So front and rear are now pointing to 0. Now let us see subsequent operations. How does that make a change, right? And how does this algorithm help with us? So if we are done with this, insert rear 20, we understood that this portion of the code actually fires when we say insert rear 20. So this portion of the code actually takes care of moving the front into front equal to 0. And this portion of the code also fires, but this portion of the code we will see in details in these set of operations. Let us see these set of operations now. Right? So if we say insert 20, okay, 20 is here. Then we say insert rear 32, 32 goes here. What happens? Rear is increased. Now rear becomes from 0 to 1. 1 modulo 5 is equal to 1. So rear is at 1, and dq rear, the array is called as dq. So dq rear becomes the value that you are trying to put, and that 32 goes inside that index position. Right? So 32 comes here. Your rear has therefore moved here. Your rear has therefore moved here. Now we say insert rear 5. So 5 comes here. Rear moves here, because now rear becomes 2. 2 modulo 5 is equal to 2. Now then we say insert rear 11. Rear moves from here to here. Why? Because 3 modulo 5 is equal to 3. So rear moves here. And then we say insert rear 34. So now we have 4 modulo 5 equal to 4, and rear moves here. Right? So that rear is right now at 34. And then we say delete front. If we say delete front, whose operation we will see later, but you can understand delete front is delete from the front. So in the front you have what? In the front you have f, right? So you have 20. F is pointed to 20. So what we will do is delete from front. So this element will not be there. So we have deleted this element and we have moved the front here. Right, so delete front means the dequeue operation in a simple queue. In a normal queue, we are talking about delete here because the queue itself is called as dequeue. Right, so delete front will move the front here to 32 and this position becomes blank. Now what happens is that you could now understand that every time rear was getting increased modulo the size of the array, which was modulo 5, and you actually positioned rear to where it wanted to be, and there you put the element to be inserted. Now if we delete front, then delete front would mean that the front here got deleted and the front moved forward. So now let's talk about the last operation, which is insert rear. Right, we are trying to insert 12. Now rear is at 4. Right, if we insert a rear with 12, then 12 will come here, but for that this rear which is at 4 needs to move to 0. Right, so how will 4 move to 0? And that's what is achieved here. Your rear is equal to rear plus 1, so rear becomes 5 because rear was at 4, so rear becomes 5. 5 modulo 5 is equal to 0. So that is what is going to move the index from 4 and wrapped around to 0, and that's where that's how we will have rear going to 0, and at 0 we will therefore insert the dequeue rear x, which is going to be our 12. Now if you understand this process, I just wanted you to spend some more time on a number line, and let me see if I can make you understand, because this will be also useful for you to understand other operations of the dequeue as we move forward. So if I just imagine a number line like this, then if you just see this number line, then this particular first set of blocks actually represent valid indexes of the arrays of size 5 for this particular array, right, that we took, right? These are the index positions. Now if 0 is a valid index position for this array, 1 is a valid index position, and so on and so forth, then what happens when 4 becomes incremented to 5? This 5 has to come back to 0 because 5 doesn't exist in principle as an index. 6 has to come back to 1. So what we are doing is whenever this particular block goes out of scope, we are going to basically take this block and bring it inside this block through the modulo operations. That's where modulo is coming to help you, right? So we will take 5 and bring it back to 0 by 5 modulo 5. We will take 6, bring it back to 1 by 6 modulo 5. Similarly for 7, 8 and 9. And that is what is happening in this modulo operation. It is wrapping the particular index position that we superficially achieved. It is wrapping these index positions into a modulo based proper index position which actually exists. And that's what typically we are doing here. So that's the dequeue operation on the insertion of an array, insertion into a dequeue, right? So insertion from the rear part of the dequeue, and it's pretty simple. So what we talked about are two operations basically. One operation was on checking the front -1, because as I said, insert rear will always handle rear, somebody has to handle front, and that's why we will remember this, that somebody has to handle front. Okay, so we'll do that first operation. Actually speaking, if you see, there are actually three things. If you want to remember the algorithm, there are three things. First, check for the empty or full condition. Sometimes we'll check for empty, sometimes we'll check for full, depending on the algorithm. Second, check for the exceptional scenarios. Front has to be handled exceptionally, we have discussed that. Third, do the actual operation, and in this actual operation, remember around modulo, because circular queue means you'll have to handle modulo, right? So that's on this. Now if you see the complexity, the time complexity of this will be an order of 1, because there is no loop, nothing. The space complexity are all in place replacements, and the space complexity is also going to be an order of 1, right? So that's on the dequeue operation on insert rear. If we move to the next operation, and we will again take the next operation as a conventional operation. So if we have a queue like this, a conventional operation of delete happens from here, and we used to call it as dequeue, right? And we are calling it as delete front because our queue itself is called as dequeue. So from that standpoint, let us see what this does. So this also has typically three things: 1 for this, 2 for this, and 3 the actual operation. In this way, you will remember, right, that the algorithms for DQ in terms of the operations will have three things. One, handle the empty or full condition. Second, handle any exceptional conditions, and the third, handle the actual condition. Now, if we say that delete front, we have to delete front, then let's take these operations, right? Insert 20, okay? 20 is inserted. This was not empty, so it moved forward, and normal insertions happen. In fact, this is insert rare, the previous operation. We have not even gone into delete. So let us insert things first and then we'll go into delete. Then 31, 26, now we have a delete front. So this delete front operation, what it will do is, my front was here and my rear has moved here. So delete front will actually take front here, and therefore this would be logically deleted, right? So this will be logically deleted. Then again, if you delete front, and how is this happening? Let us understand how is this happening, because our algorithm here is getting called. So if we say delete front, our front was here at 0, right? And we said delete front, is empty is false, right? So it's not is empty. So we say DQ front. DQ front means we store the value of delete front, whatever was here, which was 20, right? So we have stored that inside val. So we have said val equal to 20 by storing this value here, right? And then we have to move front forward. So if we have to move front forward, is front and rear the same? If front and rear is the same, then we are actually hitting a condition where we have reached the end of the queue, right? So in that case, moving it front will not help, because front cannot cross rear, right? So in our case, that is not happening. Front is not equal to rear. So what do we have to do? Front will increase by 1, and that's what has happened. Front will increase by 1. Modulo size will come into presence only when front crosses 4. We have seen earlier. I'm not going to check that again. Just last slide we had seen why modulo size is necessary. So front keeps on moving. Once it hits 4, it has to become modulo size in order to go to 0. That's what the essence of this particular line is. So in our case, what is happening? This front moves forward through this line, right? So if this front moves forward through this line, and again we take delete front from here, right? There is one more delete front. So this will also become moving from here to here, right? And this position is now empty. Now what do you see? Rear and front are the same, right? So what does the queue contain? The queue contains only one element. Now one more delete will delete this 26, and rear and front, because they are the same, rear and front because they are the same, will now have to have rear and front pointed to -1, which signifies an empty queue. So that is the special case that you are handling here, that if rear and, because we are moving front forward, at some point it might reach rear, because we are deleting elements from the front, it will reach rear at some point, right? So we are deleting, front is here, rear is here, we are deleting this, then front moves forward, we are deleting this, right? In this way, front moves forward, we are deleting, every time we are deleting. Then what will happen? Front will come here. So front and rear will be together, and at that point only one element is here. And when that element also is deleted, then the queue is empty, and that handling we'll have to do here, right? So that is your second exceptional case handling that we are trying to do. So let's discuss the next operation, which is, or rather the next example. Let's take this example and fill this up. Let's say we insert 20, we insert 31, these are all insert rares, insert 25, insert 2, insert 23, and our front is here, our rear is here, right, after this insertion. Now what we are trying to do is, we will now start deleting front. So if we delete front, because front is here, front will move forward by 1, and because front will move forward by 1, so front will come here. No need for this modulo, will not actually make any difference. It is there as a standard code, but it's not getting typically logically used here, right? So because we can typically go to 1, which is a valid index, we don't need modulo's help to bring us back from the wrap. So this will come here, front will come here, and this will go away, this will go away. So front is right now there, and now we have insert rear 34. So insert rear 34 would mean that we will move rear forward, and that we have already discussed. This will wrap around, and this will not be this will be there, and rear will now come here, right? So that's something that will happen when we do this insert rear. Now we have 3 sets of deletes. right? So these three sets of delete will take this front from here, first step, second step front will go here, third step front will go here. So let us do that in one block. So let us say that front will go here and every element will be dequeued and that will not be there. Now if we take the last operation, which is this delete, right, then this front will now go here. And how can it go here? Because now this modulo will be utilized, because 4 plus 1 will become 5, 5 modulo 5 is equal to 0, which is a valid index, and hence front will now no more be here, front will now move here, right? So that's where front will move, and this element will be deleted logically. Now that's how, or that's why this particular modulo size, front getting increased by 1, and hence this modulo size syntax is so important for you to understand when it gets triggered. And I just now gave you an example of how the modulo size syntax of front increasing and hence getting crossing the boundaries and hence has to come back to the boundary will be triggered when we actually talk about a dequeue in a circular manner. Complexity, the complexity is simple. The complexity again is time complexity will be order of 1. The space complexity will always also be order of 1. These are all in place replacements. So that's on the delete front. Now if we talk about insert front, now we are talking about the we are discussing the specific things about a dequeue, right? Till now the two operations that we discussed, any queue will have, any circular queue will have. Now we are talking insert front. No insert happens from front in a normal queue. We are talking dequeue, na? So if we are talking dequeue, then insert will happen in the front. So we are talking about that special operation, right? So let's do this. Let's see how the algorithm works. If we insert 20, then 20 will come here, right? As soon as 20 comes here, what happens is your front, which was -1, and I hope you know that every front and rear is -1 in an empty queue. So front and rear was -1, front and rear were -1, and what did front and rear becoming -1 happen? When we actually inserted from the rear, we will have to take care of rear now moving to 0, because front will anyway move, because we are inserting front, so front will anyway move through the algorithm, but rear has to be taken care of. So first step is take care of the standard is empty is full. Second step is take care of the exceptional scenarios. Who doesn't move? The rear will not move, so make rear 0 and then move on. So that is what we are doing here, making rear 0 and then moving on. And when we move on, so that this step is actually understandable, that when we do 20, rear will actually come to 0, front will also come to 0, and both front and rear will actually point here. Both front and rear are now pointing here, and they are therefore representing a queue with one element. Now so that's the index position set is happening here. Else will not fire. Dequeue will take this whatever x we have given here, this x will be going into that index position, which is 20, and that's what we will have as the part of that first part of the algorithm. This part of the algorithm, which is the actual work, let us see that also in operation. So let us say that we have inserted 20, we have inserted 34, then 26, then 31. So where is our front and rear? Our front is here, right, and front will stay there, in fact we are doing an insert rear, right? So our front will stay there, and we are doing an insert rear from 20, 34, 26 and 31. So our rear has moved here. So every time we are inserting from the rear moves by one element or one index. Now we say delete front, we have done that. So delete front is 2 times here, right? So let us do delete front 2 times, front will come here. So if front comes here, then these elements are deleted, right? So now we have the delete front gone. Then the actual operation that we are discussing right now, which is insert front 7. Now front is here, insert front 7 means take front backwards. Take front backwards, make front -1, right? So make front -1 is what happens here, right? So that's what we are doing. We are taking front -1 and making front equal to 1 and inserting that value here. What is that value? 7. So now front is here, front is no more here, front is right now here, right? And then we do one more insert front, which is taking front from here to here backwards. Insert front, now insert from the front, so it will substitute the placeholders that is left empty, right? So that's what will happen. So it will go backwards by one and it will go to this. Now if we actually say insert 13, then what will happen? 0 will become minus 1. 0 will become minus 1. So minus 1, if we add the size of the array, then we will get 4, and that is what we wanted it to be. We will get 4, and therefore 4 is what we will land up with. And that's the reason this plus size is there, right? So front minus 1 plus size, whenever you make minus 1, you will have to add it in order to make it come back to wherever it is supposed to be on the number line. We just now explained it in the last example also. So now this 13 will find a placeholder here. So minus 1 plus 5 is equal to 4, and 4 will go there. 4 modulo 5 is 4 always, right? So 4 will go there, and wherever that index position is pointing, we are dequeuing. In fact, we are putting the value of that particular x into that index, and that's what this particular algorithm is. So again, the same set of things. First, don't forget, you have to put the is empty is full condition check. Second, don't forget, you have to put some kind of an exception. We are talking about insert front, and since we are talking about insert front, we will not be taking care of the rear part of it. So rear has to become 0, and then we are talking about front going backwards. Therefore we will do a front minus 1. Front minus 1 may become minus 1 also, because when front is at 0, it becomes minus 1, and at that point we'll have to add 5 in order to bring it back into the circle, right? So that is what this algorithm is all about. Moving on, the complexity of this, we will have the time complexity for this as same, order of 1. Space complexity all in space in replacements, so we will have order of 1. Now another special operation, which is in fact in a queue like this, we understood that it will exit from here and it will enter from here. But what happens if the exit is also from here, right? Delete rear, that is what we are talking about. Delete rear, right? So delete rear, let us see what all examples we have. Let us insert 20 here. The standard set of operations is the first is the check, second is the exception, third is the operation, right? In this way you can remember things, I'm sure, and this applies to the previous algorithms also for stacks and queues. You can find a pattern there also, right? Now 20, 34, 26 is what we inserted, and with that what did we achieve? Front became here, rear became here. Now we said delete rear. Delete rear means that this is going out, right? So we are exiting, that means rear should now go backwards. Now that's strange, right? So there was always going forward, now rear is going to go backward, because this is a special operation for a dequeue. So if rear has to go backward, then the same set of formula applies here. Rear will go backward, and because backward can take it back to 0 and then minus 1, so add it with size and then do a modulo. So rear goes backward here, so let's put rear here, and we had delete rear. One more delete rear will make rear come here, and therefore and these elements will not be there, and then one more delete rear. This last delete rear will do what? This will take rear here, but it can't go there. Why? Because front and rear are the same, right? And so what we are talking about right now, we are talking about this particular second case. This example is trying to highlight this second case, right? That front is equal to rear, so delete rear makes front and rear equal to minus 1. So it will be deleted, yes, front and rear will become minus 1. So this particular line is going to simulate this particular action, right? So that's the example. Now the other set of example, if we take, then if we say 20, 34, 26, 32, 49, and then front is here, rear is here, and we say delete front, then delete front would mean that front has moved forward and these two records, these two are not there, and then we say insert rear, and that's where the magic happens. Insert rear means we have to increase this and that will be the insert rear algorithm that we have already discussed, which will take the modulo help and basically insert the rear into 22, right? So that's where it will insert, and rear will start now pointing to 0. And what will happen for this particular operation, which is our delete rear operation, right? So the delete rear operation will now need to delete this and move this rear back, right? So that's what will happen, because rear has to come back. We are talking about delete rear operation, so rear has to come back and fill up wherever it is. It cannot point to a blank position, right? Of course, so it has to come back. So if it has to come back, then we have to do a rear -1, and if we do 0 -1, it becomes -1. So we will add the size to it. We get -4, +4, and this +4 is pointing to a valid index position. In that valid index position, 49 is there, so our rear starts pointing here. That is what is happening when we talk about this third operation or third line of the algorithm that we are trying to highlight as the three things that it actually will do. So that's on the DQ operation on delete rear. In terms of complexity, if I go, then the time complexity of this is going to be order of 1. The space complexity of this is also going to be an order of 1. No loops in place, substitutions, hence order of 1. Now get front is one more operation, and it's very simple. So if the queue is not empty, then there's if let's say I have pushed 30, 29 and 6, right? Where is my front? Front is here, my rear is here, right? So get front is empty, is not going to return that. And DQ front is already pointing to 30, so DQ front will return me with 30, so that is going to be my rear front. And even if I delete this front, and move this forward, right, so this front will now come here. So now because front is pointing here, this front index now points to the DQ of 1, right? So it will return what? It will return 29, and that's what get front will return. Time complexity of this will be again order of 1. Space complexity will again be order of 1, right? So that's on the get front. If there is a get front, there has to be a get rear, right? And then the same thing, if I have inserted 29, 30 and 6, and if I have a front and rear here, then rear is pointing here, so DQ of rear, which means DQ of 2, right, will be returning with me what? 6. What is the time complexity? Time complexity is again order of 1. What is the space complexity? Space complexity is also order of 1, right? So that's typically what is there in the DQ. Is empty, we have discussed this, and only when front and rear are outside and they are not pointing to any valid element, we said if the queue is empty, and that's what we are checking when in is empty. So return front equal to rear equal to -1. Here also the time and the space complexity is going to be the same, right? So if the queue is empty, of course front and rear will be -1. All you need to check is front and rear is -1, right? Then just return it as an empty. The true value will come when you actually return that in this fashion. If is empty is there, is full, so we have 29, 6, 7, 8, 16. Where is our front? Here. Where is our rear? Here. Now listen carefully this particular example. Now what is happening is, if this queue is full, we can understand that, right? So if we can understand that, what is the case here? The case is that this rear is at 4, and what is 4? 4 is basically 5 minus 1. So can I say 4 is size minus 1? Yes. So rear is equal to size minus 1. So rear is size minus 1 and front is 0. So these two conditions will therefore signify a full queue. A full queue. So this is what is trapping that. If front equal to 0 and rear equal to size minus 1, then it is full. Now what happens if it is something else? Let us say that it is like this. What happens? It is so what happens if front and rear are here and then I start moving the elements? There could be a situation where front and rear are here, right? So somehow I have moved the elements forward and then front and rear are like this, right? So there could be a situation, there could be a circular queue which is like this, right? So I have moved these elements forward. Now oh sorry, this element is still there. This is, let's say, 47 or whatever that element was. Now what is happening is that front and rear are actually sized up like this. The only thing we can see is that the queue is full, but right now front is not 0, rear is not size -1. But can we say this particular logic then? If we add 1 to the rear, that is, we add 1 plus 1 because rear is pointing at 1. So if we add 1 to the rear, then we get 2, and that evidently is the index of front, right? So this becomes equal to front, and therefore we will have something where this particular right hand side of the OR statement will fire a truth value, and hence this is full will return true, that yes, I am full. Now why this modulo size? Nothing specific, because the modulo size is not necessary here, because the wraparound is handled through this particular code, right? So but you can keep it for consistency. If you write this left hand side, this modulo size is not necessary, but it is easier to remember it, which is why I kept it here, that okay, if you are increasing, always keep a modulo size for safety reasons. But here we had handled or tackled this situation through a separate OR statement on the left hand side. So that's what this particular full algorithm you will have to remember. Complexity, as you can see, the time complexity is order of 1, the space complexity is also order of 1, right? So that's the all operations of a DQ that we discussed. We will now touch upon priority queue, and then we will complete all the commonly asked questions for both DQ and priority queue. Now priority queue is pretty simple to understand. Yeah, instead of the queue, instead of the queue taking a decision of what to queue first or DQ first, right? That is, what to exit, what to enter, and what to exit, right? Whether it should enter from the front, back, from the entry is possible from both the directions, or entry is possible from only one direction. It doesn't care. All it cares is some priority associated to some jobs. If I say these are jobs or numbers, right? So this 30 has a priority of 3. That means in this entire set of numbers, we will say the highest priority is the lower number that we have underneath these numbers. So 10 has a highest priority, means 10 has to come out first, right? 50 has a priority of 4 and 60 has a priority of 4, means 50 and 60 have to come out last, right? So that is what priority queue actually means. So elements with higher priority are served before elements with higher priority elements with lower priority. That means you are going to service the higher priority ones, means you are going to DQ them, you are going to take it out of the queue, right? Queue is just a temporary placeholder, right? You are servicing means somebody has asked for it, you are actually giving it back. So that is called as the DQ process, and the DQ process takes care of the priority. If two elements have the same priority, they follow the normal FIFO order, and we will see that example. We will see that here only this example is there, but that is what is a priority queue. It is a special type of a queue in which each element has a priority, and that's what we are discussing here. Each of these elements here have a priority, right? And that priority is here, and we just now said that lower number means higher priority, right? So with that, if I just debrief you about what is going to happen, we are going to take two kinds of priority queue. One, unsorted array, the priority is handled during deletion, and then a sorted array, the priority is handled during insertion. What it means, let us discover it now. Now this array is unsorted. I hope you can understand. This particular array is unsorted, and we are going to represent a priority queue through arrays. A priority queue is best represented through linked list. Since we have not done linked list, we are actually focusing only on arrays now. And you can write arrays in your examination, and you can write it as a double, because we have two sets of information that we have to store. Therefore, we need two sets of arrays, right? So these two arrays will store these two sets of information. Now, when storing, if I just store it the way it is coming, then it is an unsorted array, and the priority is handled during deletion. Means that I am going to store in the first pocket 30 because it came in as 30, and for the priority array, so if we call this as the data array and we call this as the priority array, right? So the priority array's 0th index will have 30, data arrays 0th index will have 30, priority arrays 0th index will have 3, and we will fill it up in the same way that we are getting the elements from. So this is what will happen to the priority queue. The two arrays that represent the priority queue will be filled up like this. So the priority, where did priority go? Priority went into the priority array. So where is the priority getting handled now? So let us see how the priority gets handled now. Now when we are going to handle the priority means when we are servicing. When we are servicing, when we are dequeuing, right? So that is when we are exiting an element. So priority is handled during deletion. That is what deletion is also meaning, the same word deletion, right? So when we are dequeuing, exiting, deletion, all those things mean the same thing. So if we now delete an element or ask for a dequeue or ask for an exit, what is going to happen? It will handle the priority. Who is the priority here? He is the priority here, highest priority. So this will be coming out as a dequeue. Now if this comes out as a dequeue, this will go away. So what happens to all of this? What happens to all of this? They will have to shift, right? And that is where you will take a cost. You will have to loop through and bring all the elements from the right to the left, and that is where the priority handling during a deletion will have an order of n as a complexity. Right? So you will now handle that for an unsorted array. For an unsorted array, the dequeue operation or the delete operation is actually taking a time complexity of order of n. I hope you can understand that because we are going to give back basis the priority, we can give back through a loop. That is, we have to reach to the priority through a loop, and we will see the algorithm later. And we will also need to shrink the array so that it comes to a manageable, it doesn't have any blanks, and that's why we have to run a loop, and running a loop will mean order of n. The space complexity will still remain as order of 1, right? And then when we do one more delete, what will happen? This will come out, and if this comes out, then this goes away. So this entire set now needs to come back. This entire set will now need to come back. Now if we have to next delete, then the next lowest priority is this. So this this particular 3 will come out, right? So this 3 will come out, and this entire set will now come back and position itself here, and position itself, I'm sorry for that, let's see what's going wrong. Yeah, so it will position itself here. And now the tricky part is, now we are trying to talk about this particular thing, where we said that if two things have the same priority, then what will happen, right? So we will talk about that now. So if you see now, two of them have the same priority. So what's going to happen? The way they appeared in your problem statement, the same priority, the same order, they will be exiting. So they appeared as 50 and 60. 50 coming first, 60 coming later. So 50 will be released, 50 will be deleted, and then 60 will come back, and then one more delete will actually delete this 60 also. One more delete will actually delete this 60 also. That is what is going to happen from an unsorted array if you actually do the delete operations of the unsorted array. I hope that is understandable. And if I just take the sorted array now, so if I sort the array earlier, then the priority is handled during insertion. That means the array is sorted, and I am going to be careful when I'm arranging, when I'm arranging, and the array is sorted not on priority. The array is sorted particularly on the data that is actually having itself with. So what we are trying to do is, we are trying to say that the data is here coming as 10, the priority is 1. The data comes in as 40, the priority is 2. So in case this was not the case, suppose I said this was 3 and this was 2, suppose, right? Then this was this is supposed to be, this 40 is supposed to take 2. This 40 is supposed to take priority of 3. Now, when 30 comes in and 2 is here, the insertion will do what? The insertion will move this 40 to the right and make space for this 30 with the priority 2 here, right? And that way the insertion is actually taking care of putting everything in a proper manner, so that when we are saying deletion, this item will come out and this item will come out, right? So deletion means delete from the front. No need to actually move the items to the left. Again, the next deletion will delete this and this will come out. So it will delete this item. Front and rear will move forward, and therefore rear is already there, front will move forward because you are deleting from the front, right? So when you actually place everything in a sorted manner, deletion becomes very easy. Whereas deletion in an unsorted array was taking an order of n. So what is not easy for a sorted array? So for a sorted array, what is not easy in terms of time complexity, is that the insertion will have to take care of pushing the elements to the right so that you can insert it in a proper position. So the insertion will take a time complexity of order of n, because it will run a loop to push the elements to the right, and then one block will be created empty, and in that block it will place the appropriate data, and then we will have the Sn, which is the space complexity, which will still remain as order of 1. So that is on the priority queue. Let us see an algorithm. I think it will be clearer and we will only talk about the unsorted array in terms of algorithms, because that's the most commonly academic example that we can think of. So in this case, the data and priority are these two arrays, as I said, and what is going to happen is this 33, 10, 50, 40, 60, all of these are there, and we are now going to insert this step by step. So insertion will be blind, right? Insertion is not going to take care of priority. The deletion will take care of priority. That's what we know for an unsorted array, right? So what is insertion going to do? Then first thing that insertion will check is the full case. If it is full, I'm not going to allow you to insert, right? So that's the full case. Now what will happen for the rest of the thing? We will maintain a count, which is the index. So count is actually 0 initially, right? So when we say count is 0, then data of count, when 30 comes in, data of count is data of 0. Data of 0 will become 30. Priority of 0 will also become 3. So data of count is value, priority of count is PR. That's what we did just now. And then we will have to increase count by 1. So count becomes 1. Count starts pointing here. Next time the data comes, which is 10 and 1, it will be 10 and 1. Count will become plus 1 again, which is 2. Next time the data comes, it will be 50 and 4, and in this way it will go on, right? So this is the insert. Simple code, simple loop. You have done it many times. Nothing to explain as much. What is the complexity? Complexity, time complexity is order of 1 again. No loops. Space complexity in place is there. So we have order of 1. So that is what will happen when you are doing insertion. Insertion is very easy in terms of cost, because it is an unsorted array. I'll just take it and insert it. I'll not worry. Who will worry for it? Deletion. So let us see deletion. So deletion will worry about checking for which is the lowest priority. So first what it will do, it will check for the standard stuff, which is the queue empty. If the queue is empty, of course it will return. Otherwise, what it will say is, it will take an element called highest. The highest will have the priority where this priority is lowest, right? So it will have the element with the priority lowest. So it has taken highest as 30. So it will take the first index position, which is 0, as the highest. It will assume that 30 is the highest priority, and then it will run a loop. It will run a loop and it will replace this highest, go forward and replace this highest if the priority is less than that of the highest, right? So if the priority of the highest if the priority of the highest, in fact highest is not 30, it's the highest is priority of 0, so it's storing priority, not the value. right? So we will store priority which is 3, and we will check the next priority is 1 which is less than 3, so highest will become 1. Next priority is 4 which is not less than 3, so 1 will still remain. Next priority is 2 not less than 1, so this will remain. 4 not less than 1, so this will remain. So we got our highest priority as 1. And where did we get our highest priority? We got our highest priority at a position of 1. So the position is also getting tracked where we are getting this highest priority, right? At the beginning the position was 0 because we were pointing to 0 as we were assuming that 0th position contained the highest priority. Then we went through this loop and we increased the position. Wherever that position was there, we actually found that position and we stored it inside position. Now we know that this is the highest priority, so all we need to do is push these elements to the left, right? So we will print this first because this is what we had to delete. So we will send this to print. We have this already stored here, right? The highest priority, the position. With the position we will print the data, right? So we will print data bracket position and the priority, right? And then we will shift all these elements to the left because this work is done. So we have to delete all of this and shift all of this to the left. How will we do it? We will run a loop from position. Position is pointing here, so we will run a loop from position less than count. So position will go from here to here to here to here, and each time what it will do, it will say data of this particular I, and position is basically the value of I. So what is happening here is it starts from position, so I equal to position, and then this is I plus plus actually. So it actually shows that position is increasing, but yeah, position we are maintaining here, and what all we are doing is we are saying I plus plus to move forward. So if we say data of I, then data of I is right now at position, and that will be becoming equal to that will be becoming equal to our data of I plus 1, the next data. So that means that this gets stored now here, this gets stored here, right? And similarly we'll have to say priority of I is equal to priority of I plus 1, same way, right? And that's what we will do. So once this loop gets over, this will go on, and every time it goes on, I has increased. So right now this 50 will have come here, 4 will have come here, then 40 will come here, 2 will come here, then 60 will come here, 4 will come here, and in this way the loop will end, and therefore you have deleted highest priority and you have moved the rest of the priorities and made the array aggregated together. What is the complexity? The complexity of this is going to be, for delete it is going to be an order of n, because you are running a loop. To do it, space still will remain 1. There is no necessity for actually taking anything which is an array or which is dependent on the size of the input. So that's on the priority queue operations. The rest of the operations are pretty simple enough. We will go quickly through that. Again, in an unsorted array, if this is the data and priority, then peek is an operation which will not delete the highest priority. It will still be there, but it will be sent to a print. It will be sent for a print. So the same algorithm will run for delete that we saw. Only thing is that last loop where it was being shifted, this last loop is not going to be there. This is not going to be there. Then it becomes the same algorithm. All you are doing is you are trying to find out which is your highest priority, and you are printing that highest priority element. That's what, data pause and highest. It's the same code as the previous code. The complexity of this particular code will be time complexity, because you are taking a loop, you will have an order of n, and space complexity will be order of 1. Now is empty, there is also going to be an operation called is empty. If the count is 0, remember we took a count and we moved count forward. If the count is 0, the queue is empty. Is full, if the count is equal to size, of course it is full. So now let us move to the next topic, which is we finished off with the priority queue also with these 3 operations. And our next topic is going to be around solving the common set of questions that are asked. Most of the things have been discussed, so I think there should not be much. Which of the following data structures allows insertion and deletion from both the ends? Now you know. There is a typo here, and that was the same typo in the question paper also. It's a copy paste from the question paper, but you can understand this is a DQ, and DQ will have insertion and deletions from both the ends. So this is the answer. Write short notes on DQ and priority queue. We have explained it at length. So depending on the marks, you will have to probably answer what you want to answer. A linear list in which elements can be added or removed at either end but not in the middle is a DQ, right? Let me write this here. What are the types of queues? We know the types of the queues are a linear queue, we have a circular queue, we have a DQ. And we have a priority queue. So these are the types of the queue. These two are covered in the last lecture. These two are covered in today's lecture. So you can explain all of them by going through the problem statement that is there. Typically, if this is, each of them is supposed to have, let's say, 2 marks, then just explain or draw the queue and explain or write the operations. What are the operations of it, right? Just write the operations. No need to explain those. If it has large marks, if each of these has 5 marks, then I would suggest that you define the queue and you explain the operations also, right? So you define the queue, what this queue looks like, what is the definition, right? And then you also explain the operations. Write the operations, 1 line on the operations. No need to write the algorithm unless they explicitly ask for it. A DQ can be used as a stack, as a queue. Yes, we know they can be used as a stack and a queue. I explained that. Both as a stack, as a queue. Yes, right? So basically the answer should be C, right? What is a DQ? I think this is a theoretical question. You can answer this, and that's all that comes from this particular chapter. So if you see the priority queue, typical question is not on any problem related to a priority queue. It is mostly around what is the algorithm or what is the definition of a priority queue. DQ also, there is no specific example of what will happen if this is pushed or this is deleted or this is inserted from rear, from front. Nothing of that sort is noticed in the last few years of university questions. So you can probably just take this particular chapter with the thought process that mostly theoretical concepts will be asked, short notes, definitions, and worst case you will be asked for operations, right? So that's on DQ and priority queue. We will cover linked list, and with that, before covering linked list, this completes what we intended to cover as a part of our stacks and queues, and as such this completes our module 2. So module 2 will be covered or is complete after today's lecture. Next lectures will be around linked list and trees, and that's something that will be pretty exciting because that's where you will see a lot of convenience that we'll get beyond arrays and a lot of applications that you will get to learn that arrays cannot typically handle, right? Till that time, have a nice time, start studying. Exams might be near depending on the time when you are watching this, and have a great day ahead. Thank you so much.